Hi everybody, welcome back to another IBIPS Education webinar from our series on occupant-centric simulation-aided building design, which is based on the book, which is available to download. I'll pop the link for the book in the chat as we go through this session. Today we're going to be talking about fit-for-purpose occupant modelling with Ardeshir Mahdavi. So I'm delighted that you're able to join us and thrilled that we can have such an illustrious presenter today. The format for the webinar today is going to be the same as usual. If you've been to one of these sessions before, it'll be very familiar to you. In a moment, I'm going to invite Ardeshir to share his screen and start his presentation. Once he's finished presenting, we will have questions and answers. If you have a question for Ardeshir as we're going through them, please, you can type it into the question and answer box, which should be at the bottom of your screen, and then I'll put the questions to Ardeshir at the end of the presentation. Like all of our sessions, this is being recorded and it will be available on YouTube probably tomorrow. This webinar is presented on behalf of the IBIPSA Education Committee, and the IBIPSA Education Committee's role is to identify education and training needs throughout the building simulation performance community, and that covers a very broad range of people involved in building simulation. Part of our objective is to initiate and develop and encourage new education materials and methods. And a really key thing about sessions like this is that they're open to non-members as well as to members. So if you've got any ideas about things that you would like to see in future webinars, then do please get in touch. You can contact me via the sign-up link that you had or on LinkedIn, and I'll share details about that after the presentation. But for now, I'd like to invite Ardeshir to share his screen and to start his presentation. Great, thank you.
Great, thank you, Pamela. Very happy to have the opportunity to share with you some thoughts about the subject of occupant representations in building performance simulation, and with a special focus on the aspect of a representation being proper for the purpose of the query that we use simulation for, and that we typically refer to that as the notion of fit for purpose. So let me just dive into this subject by going back to the basics. Typically, when we generate a simulation model for performance simulation, building performance simulation, specifically focusing here a bit on the thermal performance simulation. Of course, there are many other important areas of building performance simulation, as you are aware, visual aspects, acoustic aspects, and air quality and all of that. But for the sake of argument, we focus now on the thermal aspects. You generally have to have multiple streams of data introduced into the building model as input information. This includes basically the static components of the building, let us say the building fabric, construction, materials, and so on and so forth. And of course, modern buildings usually deploy the services of some kind of a system, environmental control systems for heating and cooling and ventilation and lighting and on. A third stream of data that we need to provide to the model is the contextual information, most prominently the weather conditions, the climatic conditions, but we also have to increasingly address the urban settings, the site conditions, and so on and so forth. So these are kind of external conditions. And last but not least, of course, we have to also map the internal processes that are going in the building into the simulation model. And since most of the building, the overwhelming majority of the buildings are built for human occupancy, we have to also map information about the occupants in our simulation models. And Once we have all of that information, we can subject it to a mathematical processing using typical algorithms, in this case, for example, heat transfer, and use that results in order to build up the values of our performance indicators, multiple kinds of performance indicators related to indoor environmental conditions, thermal conditions, temperature, distribution, but also energy-related indicators in terms of the loads for heating, cooling, and energy consumption. So that's the basic scenario. And in the building performance community research and application, this notion of modeling the human users of the building is, if you want, historical, an area which has only more recently attracted specific attention. We have always done that, but the way we have done that has gone through some evolution, which is maybe worth reflecting upon. So again, going back to the basics, peoples obviously influence the performance of buildings. I once referred to the two types of effects. We can generally refer to the passive effects. Those are effects that by the sheer presence of people in the building occur, even if they don't do anything, just by their presence, as long as they're alive and breathing. For example, in thermal settings, they introduce certain thermal loads, sensible and latent thermal loads, but they also introduce carbon dioxide, other type of air pollutants, and so on and so forth that need to be taken into account when we're talking about the temperature evolution in the building or the ventilation rates that are required. But we are focusing on the thermal aspects, but the presence of building has also effects on other areas. Just to give you an example, in acoustic terms, the presence of people and their clothing ensemble affect the sound absorption in the room. It's very important in cases people design rooms that are critical in terms of the auditory aspects and communication, music performance, and all of that. So it's very big differences between the reverberation times in an occupied room and in an empty room. But there are also these active effects. Active effects, we can think about interactions of building users with the building control elements and systems for lighting, for shading, for temperature control, and use of electrical equipment. All of that interactions obviously have also ramifications for the transfer of energy, the energy flows in the buildings, and the derivative requirements in terms of the provision of heating, cooling, and ventilation. Even in the area of acoustics, people's behavior affects the acoustic. For example, if you're familiar with the Lombard effect in the acoustics, if you're in a loud room, you start to talk much louder, and people do that in a way that it affects the overall acoustical environment in a massive way. So all of these, if you want, facts underline the importance of our methods in representing people. And if you want, historically speaking, there was also an additional factor that encouraged additional reflections on the topic, and that was when people started to talk about the energy performance gap at some point a few decades ago. And that discussion, that discourse was motivated by the fact that we figured out that we make predictions based on performance simulations, and that predictions in many cases involve errors, and there's deviations between expectations and the reality as it is that can be monitored. People refer to that as a gap. In case of energy predictions, energy performance gap. And for some time, colleagues were kind of suggesting that this gap, or at least a major fraction of that, is due to insufficiently accurate representations of people's presence and actions in the building. Of course, this is a tricky subject. I've just quoted here a paper, a recent paper that I wrote together with my colleague Christiane Berger. You can refer to that. So we have to look at this issue of the performance gap a little bit more differentiated way. It is not as straightforward. But the point is that that discussion is at that time provided a motivation to reflect about, okay, how do we actually model people in typical applications quite common in energy simulation. And one of the arguments was that those representation of people in terms of, for example, fixed schedules of presence or loads associated with those presence, or simple rules that would capture certain assumptions about when people would engage in certain actions. So the criticism was that those representations are too simplistic. I remember once one of our colleagues in one of our meetings suggested we model people kind of as a sweating light bulb. So, and the idea was that we just put some numbers for the metabolic heat rates and sensible and latent heat emissions, and that's it. And the corollary to that, or the counter proposal, was that no, we need to make this much more detailed, much more realistic. So we have to apply probabilistic methods and use those detailed in order to approach a more accurate, so to speak, representation of people. Again, this is a somewhat complicated discussion, and in those type of discussions, the questions that I had to deal with is, okay, is it so that for every type of application of a simulation model, should we, so to speak, aim for the most detailed or the most sophisticated and the most complex modeling approach, independent of what type of questions we are asking? So that discussion was quite interesting, and the result of it is something that we still, so to speak, deal with it. And I still have these discussions with the colleagues, and I would like to share some of the reflections emerging out of that discussions with you. So when we talk about simulation purposes, what do we really actually talking about? And most of you use simulation, you know that you can apply simulations at a very micro level, talking about the building detail. You know, if you do a thermal bridge analysis or the type of emissivity of a material and how it affects the surface temperature and those type of things. So you were talking about a very focused and physical aspects of the building performance. That's a different scenario than when you look at, for example, a whole building. And your task is, for example, to optimize or at least attempt to find the configuration of geometry and materials and opening and envelope characteristics and glazing options. You would like to use the capacity of simulation to model these physical processes in order to arrive at some inferences as to better designs that would theoretically perform once constructed. You can apply also simulation to model these aforementioned technical systems of buildings, HVAC for heating, cooling, and so on and so forth. More and more, we also have explored the potential of simulation applications in the runtime of building operation towards supporting the building operation. We use model predictive control or other forms of simulation assisted building control. We can also expand the scale and start talking about whole neighborhoods and urban microclimate and urban energy modeling. But simulation is also sometimes used for totally other purposes, be that appropriate or not is a matter for another discussion, or for the building certification processes, for demonstration of compliance with certain standards, or if you want, for rating systems and so on and so forth. And we sometimes also use just simulation in the course of competitions for architectural designs or promotional, and of course, many of us who have academic responsibilities, we also use it for educational purposes. So if you think about this in the conceptual terms, you can imagine these various dimensions be kind of constituent of a kind of a simulation application space. And you can imagine that every query that we can imagine can somehow be placed in this multi-dimensional conceptual space of the type of things that we do when we use simulation. It could be, for example, the dimensions of from early design to building operation. We can think about addressing aspect of the temporal resolution, talking about sub-hourly or hourly simulation intervals all the way to whole life cycle and multiple decades. Then the type of indicators that we can expect in our results could be very different. We can think about peak heating loads or annual heating demand, or we'll be interested in thermal comfort indices, or those type of occupant-centric performance indicators. And the spatial resolution can also be very different. We can model the building as an entire entity, so to speak, a single node, or we can go to the level of individual workstations in an office building. So you get the point. So the point is that these variety and divergence of these very different application scenarios just imply that probably there is not a solution in terms of the resolution of the models that we apply for the entire building in general, and for the occupant representation in particular, that would fit all of these very diverse scenarios and would be the optimum approach. So the entire discussion of the fit for purpose in this case emerges from this, what I would suggest to be a logical inference. To give you just two very simple examples and to show this, so to speak, spectrum, just think about somebody doing an energy certificate. I'm not quite convinced we should use simulation for generating energy certificates, but grant me that as an example. It's being done sometimes. Okay, so in that case, maybe we are not interested in a very detailed system modeling. We're just mostly, basically are moving towards specification of the thermal quality of the building, rather than seeking predictions, specific predictions of future energy use. As opposed to, for example, when we use simulation in order to get enough data to make decisions about system sizing, the number of elements, the sizing of the elements, and issues that emerge from those also in terms of the operation. So they are very different, if you want, scenarios, and they are kind of opposite corners of this spectrum of the possible adequate resolutional representations. Sometimes I think it's a good idea if we just step out of our field and look at how it is done in other fields. So it kind of put our way of doing things in a bit in a perspective. Think about the specifications of cars' fuel economy as to the automobile industry does it. So when they, for example, provide something as an information with the cars that they are promoting in terms of fuel efficiency, for example, in terms of miles per gallon, on how many liters of gasoline per 100 kilometers or something like that, basically they are not predicting the future any use of these artifacts. Because, as you know, these numbers are typically derived on the very controlled setting where you have a automated situation that kind of quasi operates the car during a set of sequence of sessions, and it's totally irrelevant actually to real conditions when the external boundary conditions could be very different, where you drive the car and under which conditions, under which kind of road, and actually who is driving the car, which is in this case the user behavior. And you can imagine that those factors, how long, by whom, in which conditions a car is driven, it makes a lot of difference in the actual energy use. It's not quite identical with our situation in the building industry, but there are, so to speak, some analogies involved that we have to keep in mind every time we think in a very dogmatic way about the purpose of simulation being very accurate predictions of future performance of the building, even if we strive for that. Now, when we're talking about this matching of scenarios with the way we go about generating the models, it may be useful to think about a very simple, as simple as I can think of the impact of the resolution. So the decisions that we make about the size of the intervals in time and the size of the elements in space. So this is a simple example, is about the intervals, hourly intervals that we assume during an annual simulation, hourly simulation, where we have for example, we have the choice of representing these intervals in terms of 1 hour or maybe half an hour and also 15 minutes. So in this simple case, so the scenario is that, let's imagine we have a monitoring system that decides if an interval is occupied by people or not. And let's assume we make a simple rule and we say, if during 50% of the interval, this interval was occupied, then we get very different results based on the size of the interval. If you go with a 15-minute interval, your assumption will be that there's 65% occupancy over time, let's say, working schedule in an office. If you go for a 30-minute interval, you might have 60% of occupancy, or by an hourly interval, you get 80% occupancy over the simulation period. So they are very different, as you see, and they're just a simple consequence of what was your decision in terms of the size of interval and the rule that you opted for when you decided how do you define an interval being occupant or not. So we can take that example and extend it in very different directions. And none of that says that one specific decision is the correct one and all the other ones are wrong. Is also, you cannot infer from that observation that the best solution is always the maximum resolution. You have to go to not only 15 minutes to minutes, and we have to go to seconds and nanoseconds and so on and so forth. So you get my drift. So in that sense, this is a the discussion does have to be had in a differentiated manner. There are some suggestions conceptually that we should think about these two aspects, namely the resolution of the model, the complexity of the model, and the errors that we expect in terms of prediction in a, so to speak, nonlinear way. We have to think about it in a nonlinear way. We shouldn't assume that the higher complexity, the higher resolution, higher level of details automatically translate into a higher predictive accuracy. So here there are these type of conceptual schemes introduced in the literature that basically, I'm very careful about that because as with all these schemes, there are lots of, exceptions and everything. But the idea, the general idea, conceptual idea is that once you increase the model complexity in terms of geometry or temporal resolution, you obviously reduce the errors because you lose less information. So the abstraction that you do, if you do a very, so to speak, large scale and model without details, that abstraction's errors would be reduced when you increase the complexity. But then you introduce successively more and more input variables for which you might or might not have sufficient information. So in a sense, the argument is that you increase the uncertainty, and it might be that that, in fact, has potentially a negative impact on the fidelity of the simulation result as you expect. So it seems like a kind of a complementarity, if you want to use a term by Niels Bohr, so that you cannot, so to speak, maximize both at the same time. And the techniques to find that sweet spot where you say, okay, this is it's detailed enough, but not more than needed, and it has enough input variables that you have to be taken into account, but not more than that. That would give you a area and a degree of resolution that would be fitting for that specific purpose. And as I discussed before, it might be very different when you're doing some kind of a energy certificate analysis versus a building operation. So that is something that could guide us. And I'm very cautious to say we should not take these schemes as some kind of a general truths, but it helps to conceptually approach the topic. Now, in order to give you some real-world examples, I worked with colleagues on these topics, and we said, okay, we predict various things when we apply simulation. One studies we looked at prediction of plug loads for equipment in office buildings, where we had, in a specific case, measured data over multiple years. So these are example of those, and you might see that we had measurements. Here is in the blue, if you can see, and we have a simplified model, and we had a stochastic model, which was much more, if you want, detailed and complex. And then we compared two indicators, annual plug loads and peak plug loads, that would be the maximum occurring at a certain hourly basis. And it was quite interesting, because when you look at the annual plug loads, the simplified model was working very well. It could capture the entire trend fairly reliably. The other methods, especially stochastic method, didn't work as well. But when we look at the peak loads, which is a confluence of factors that's happening, happens to be a lot of occupancy and some meeting going on and so on and so forth, we could see that in this case, the stochastic model displayed a superior performance. Really interesting. So you could see that, again, I do not want to generalize this as a general rule, but it seems that a specific type of query that is looking at a performance indicator that very naturally seems to require an attention to detail and processes that are probabilistic, maybe more or less likely, versus a case that you try to get a tendency, a general tendency, a cumulative value, an aggregate value over a longer way. And depending on the type of query that you had, maybe one or the other model would be more appropriate. Here's another example. In this case was some studies we did with regard to the operation of windows. So the idea was to predict the window opening behavior of people. These are natural ventilation scenarios in an office building. Again, we had relatively detailed data about the actual people's behavior and the various predictions of the models. And in this case, the results also were quite interesting. So on the left graph, you see for various, if you want, indicators, descriptors of behavior of window states, like how reliable were the predictions in terms of the opening actions, the number of actions, how long the window was open, what was the duration. And we could see that here there was no added value in applying stochastic method or probabilistic methods that we use here in this case. The errors at times were quite extreme. The right graph shows it after we calibrated these models with the local data. That means we use some of the data to calibrate the model, and then we see, okay, the performance of these models improved, which also at that time suggested to me that specifically the models that either use learning methods or black box or otherwise probabilistic models, that they can be fairly useful in cases, for example, building operation, where you have ground truth data that you can use to calibrate that model. So again, you have a trade-off. You can get a model which is very complicated and can be adjusted to a specific setting that performs very well. But if you take that model out of that biotope, so to speak, and put it somewhere else, then it needs to be entirely recalibrated from the scratch, because it is not, so to speak, a universal model. And this high level of detail is compensated with this local, if you want, over-determination. And those are the issues that we observe when we apply these models. I would try to maybe, that space that I talked about before, is simulation query space, I try to maybe a bit more clearly describe it, in a sense that I reduce it really very much, just for illustration purposes. And I submit to you, assume you have this space, not only two dimensions, the temporal resolution and the spatial resolution of the model, So the temporal resolution could go from low to medium to high. So is the spatial resolution. For example, we could have an annual or monthly simulation, very low temporal resolution, or hourly resolution, or we go to sub-hourly resolution, or even event-driven modeling approaches. And in case of spatial resolution, again, simple example, we go from whole building to having individual spaces in the building, and to go to workstations and microzones. And if you take that very, in this case, really, large scale, very gross model in a sense, and we try to map that into queries, just for the sake of illustration. If you had a building code compliance, we probably would be totally sufficient if you have an annual simulation at the level of whole building. Maybe we could give us a little bit more leverage and do hourly simulation for specific rooms, but that would be all that would be necessary. But if you want to go into a building design, retrofit, optimization, those type of fine adjustments, then you probably would be better in shape if you would opt for at least hourly simulation, at least at the space level, but maybe even somewhat more detail. If you would go to a building systems design scenario, then it would be maybe even a final decision with regard to the intervals of time and space would be adequate. And finally, if you're talking about real-time building controls application, then maybe we should look at the event-driven processes and go for that and use that type of resolution. If I take the same pattern and apply this notion of the utility of probabilistic methods, when they are more likely to be useful in application, we can do the same spiel if you want. So we say, if I'm talking about code compliance scenarios, then maybe stochastic models really do not make a lot of sense, do not have a convincing utility. If I talk about building design and retrofit, okay, I can use them, but I'm not quite convinced that their application is crucial. When you go to building systems design, when we're talking about this issue of differential loading, dependency on the occupancy or the weather patterns that could be extreme, that may be more useful. And of course, again, when we go through real-time building operation, then that may be even necessary. So what I'm trying to, so to speak, pontificate here, if you want, is that we have to have this very open mind and have this flexibility and differentiated view of what is fitting for what time. If you do research like I do and your colleagues, and of course at that level of research is many instances where we have to go to very high level of details and even go beyond the realm of just simple thermal domain or simple presence of people. Maybe in terms of behavior modeling, we need to look at the psychological aspects and physiological aspects and the cognitive load of people and social interactions. In that case, it would be not only appropriate, but maybe indispensable that we look at formalism such as agent-based modeling, which requires that real-time interaction and it requires a lot of data. But you use that not for the, if you want, routine applications, but you're using that in order to address some very specific research queries. So you have this supervision of looking at the controlling, what is the quality that you're targeting and why you're using a certain method, and also are you prepared to address all the complexities that involve poor data quality, uncertainty, and the truthful, or let's say realistic modeling features of humans' real-time interactions in buildings. Okay, so let me summarize some of the main points of this discourse I was sharing with you. So we can apply performance simulation for multiple purposes, and modeling is not always, many times, many instances above prediction, but not always. There are also a lot of other meaningful applications of simulation that do not involve necessarily, or do not, let's say, make or break based on the matching of the future results and the current results. Because those especially in case of buildings, because of weather conditions, because of the nature of human behavior, they cannot, and I would dare to suggest that they cannot be predicted beyond a certain, let's say, statistical uncertainty level. Also, the temporal and spatial resolution of simulation models should correspond to the purpose of the modeling, which was the basic, so to speak, message of this whole discussion. And as with the whole models, also this occupant models should logically follow the same principle and take into consideration what kind of building typology, what kind of a use case scenario, and what kind of empirical information, what kind of ground truth is available to justify the level of details that we introduce in the occupant models. And finally is the complexity of the mathematical formalism and the sophistication of the tools is very useful in many types of queries, but it doesn't necessarily and automatically translate into more reliable and useful results. So that is another selection that has to take the correspondence of the task and the resolution of the model into consideration. So let me apply this issue of fit for purpose to my own discussion with you and say, was this talk fit for purpose? Well, I must admit that this talk really is not quite a comprehensive, detailed account of the chapter of the book that Pamela referred to. So in that sense, it's probably not totally successful. And it's also, and I have to be very careful and fair to the authors of the chapter, it's also not necessarily the accurate representation of all the co-authors' positions. It was mostly, so to speak, my specific perspective, but I hope that I did not falsify, their views on the subjects. I'm sure this will not be the last discussion we had on this issue. Well, I hope that I could, to a certain degree, introduce the nature and relevance of the problem, but I let you be the judge of that. I kind of followed my favorite philosopher, a compatriot, Ludwig Wittgenstein, that once said, don't get involved in partial problems, but always take flight to where there is a free view over the whole single great problem. In this case, the fit for purpose issue, even if this view is still not a clear one. I think we have more clarity than we had maybe a couple of decades ago, but it is an area which still requires attention and is probably also not as simple, straightforward of saying you just follow these rules that you be okay. This is one of the points where you need the science of the simulation, but also maybe a bit of an art of simulation, which comes with experience. Thank you very much for your attention.
Thank you, Ardeshir. That was great. And we have some questions in the chat already. The first one, I think, relates to your point that this is perhaps about the art of simulation, and that comes with experience. But are there any ways that you can get around that? Are there any programs or websites that can help to make that assessment about when to apply different simulation approaches in order to have better and more accurate outcomes?
Right. I think one of the sources of information, in fact, if you would like to go a little bit more into the detail of saying, can we technically do something about this? The chapter actually has a bunch of resources. Isabella Gaetani was the main author of the chapter, worked a lot in this area. I would not say that she developed a kind of expert system, but it went a little bit in that direction. Okay, can we formalize the most common patterns in terms of the application scenarios in a way that they can be maybe accompanied or accommodated with a kind of a rule-based system or even an expert system. And so it would be, there is some literature about that if you be technically interested to do that. beyond this notion of, okay, learning by experience and so on and so forth. I personally, I shouldn't say I am opposed to this position, not at all. I think everything we can do in that area, but I think maybe a residual skepticism, and that comes from the fact that I see another, so to speak, trade-off. Once you start to impose certain, if you want, differentiations, decisions to a system that is working based on either set of rules. Today, we would reapproach that again with machine learning and all kind of ways to say, okay, let's do a research and see how experts do this and then learn from that and apply that. We can do all of that, but I have a residual skepticism because for me, the purpose of this talk and a lot of approaches in my teaching and research is I'm interested to understand phenomena, to understand how things work, and not just have some kind of a black box that does it for me. Okay, so for me, it's not quite satisfying to say, yeah, okay, we can develop a program that, looks at the purpose of the model, you type it in, what's your purpose, and you have an initial model, and that model tells you do this and that. If you talk to experienced simulation experts, they probably would share part of this skepticism. But it doesn't mean that as a research paradigm, it is to be scoffed at. No, it's quite interesting. My point was here to suggest that consider, get rid of certain presumed assumptions like, okay, the more the better, right? The more input, the more resolution and so on you get better. Get rid of that and say, no, it's not as simple as that. So reflect about why I'm doing this and what is the information that I have at my disposal? Where does it come from? What is the uncertainty involved? And so that you'll be able, in a sense, to say the output that I get maps to this input, and it is only valid for that input. So I have a model that I know how to use. I have some input data that are very transparently exposed, and that gives me that information. If we lose that, so to speak, connection, then I think we cannot really trust our results that much, and to which extent they're useful.
Thank you. I think that's a very interesting answer. So in response as well to that question, if you have a look in the chat from earlier, there's a link to the book which you can download for free, and you can have a look at that as well. But obviously, as Ardeshir said, any of the prescriptions are no substitute for careful thinking about your particular case that you are exploring. So now we have a question about some of the results that you were presenting when you were talking about cases where stochastic and non-stochastic models were compared, and sometimes one seems to be working better than the other. Could you explain a little bit more about the type of stochastic models that you were referring to on those slides?
If we talk about the type, I assume it means if it's, for example, a Markov chain type of model, or there were multiple ones. So at some point we have even, for example, in case of window operation, and I don't want to talk about the specific authors and their specific models, because my point wasn't to say that some models are better than the other. I guess my point was that even that is not a simple decision, because the models are usually derived from a pool of data. And in our field, unfortunately, the density of data is still also kind of limited. So you develop a model based on, especially at the start of this process of we starting to work with probabilistic methods. So people get, a building or two buildings, and then they would monitor it for some time and then use that data in order to get a formalism like the Markov chains, and to try to get predictions based on that, and then they would compare it. Sometimes my criticism was that they seem to be comparing the results again with the same pool of data, not exactly the same, but you know, the drill is that you take some percentage of the data. And the problem is when we took those models independent of their pedigree in terms of what specific formalism was used, we recurrently will see that problem. So we would see that once they're encountering new sets of data, then the predictions, so to speak, goes off and they're not reliable anymore. But for example, for the window operation model, we actually looked at different window operation algorithms in literature. They are associated with the colleagues who introduced them, but I do not want to name them because my point was not to say if they are not good or bad or anything like that.
I think perhaps it might be helpful if the questioner wanted to refer to the paper. They could look at that in some more detail. I don't know if you have a link for that paper. We can share that afterwards as well on YouTube.
I just, beyond that, I just wanted also to maybe mention the IBIPSA handbook, which is an additional source of information. It had multiple chapters. One chapter was specifically about the occupant. So there's a lot of literature about this. The point about the literature, just maybe additional point, is that in many cases these models are described, you know, maybe one after the other and so on and so forth. Some of the models are already integrated in some classical simulation programs, and that's good. If somebody wants to do sensitivity analysis or so, but I think we need to do a better job to say, okay, this model was developed based on this type of data, this type of location, this type of distribution of people, because especially behavioral issues can be very different depending on the location and the culture and the type of building and so on and so forth. But the IBIPSA handbook would be another also possible source of guidance.
No, thank you for that. You can also look out for the webinars recordings from the handbook, which are available on the YouTube channel, and I'll give you a link to that shortly. The other thing that you can do is you can sign up for the next webinar in this series, which is happening shortly, and which is going to be Fahang Tamisabe, who's going to be talking about advanced simulation methods for occupant-centric building design, and that's on the 30th of May. I'll give you a sign-up link to that shortly. And now we have a question where someone is asking for some advice. I wonder if this is asking a question for a friend or asking for themselves. But the question is, if a PhD student is starting his research on psychological and behavioural factors affecting indoor exposure, how do you think he can support the latest gaps in the industry in terms of filling the gaps or verifying existing models and theories?
Oh, that's a very interesting question. Of course, one can take it in different directions. One issue is not so much the simulation, let's say, instruments as such, and the algorithm that we use, for example, to physically model the performance of the system, or in strictly physics. We're talking about thermodynamics, for example, and not psychology. But the interface to people and psychological issues are twofold. The one fold is what I just tried to address, which is, okay, buildings are influenced by presence of people, and not just as light bulbs, sweating light bulbs, but as living, breathing, acting people. And so understanding or having a better understanding of under what conditions people are compelled to do what kind of actions, it could refine our knowledge of not only building simulation, but the buildings themselves. My examples are if user interfaces of the buildings are designed in a way that they hinder fluent interaction with buildings, or they discourage people from doing the right thing, and so on and so forth. So that's one aspect. But there is also this aspect of what conditions do actually people want, or what conditions are adequate for human occupancy, because those are classical input assumption in simulation. If a simulation expert is merely a physics expert or a mechanical engineer, they need to get that information from someone. We have certain guidelines and standards that say that is the temperature range that would be appropriate. But how do we know that? Is it always like that? Is it everywhere like that? So we have been working with a number of colleagues, and we looked, for example, critically at standards that usually provide those mandates. And we figure out that in many cases, they don't provide, so to speak, the evidence. Where does it come from? And when you start to look for it, you go into kind of this rabbit hole of you are sent from one reference to another, and at some point you end up with some very old. So my point is, I think there's a lot of value in a PhD or research work that addresses, do we understand properly the human needs, its ramifications, what the desirable indoor environmental conditions, exposure conditions, because they are needed as input to the simulation models. And so there would be one way of refining and making use of that information is that. So, for example, if that colleague, he or she would be my student, I would say, okay, what is your general direction? Are you thinking about using that information gained from better understanding of human psyche and desire to behave in terms of better understanding what are the people needs? Do you would like to have better system feedback, better interfaces, people interacting with buildings, knowing more about people? In that sense, do you want to maybe enhance the operation control systems of building in a way that they are more responsive to those type of requirements? So there are a bunch of, I would say, noticeably useful results that can come out of those studies. But I was warned that no one single study can address all of that. So the research world is a collective endeavor. So do not try, if I would recommend that to my students, to solve all of their problems at once, but look at a certain specific question that would fit in the puzzle, and in the long run support the community for assuring buildings that have a better quality for their inhabitants.
Thank you. I think that's incredibly useful advice. There's a lot of really exciting research out there still to do. One thing when you start working in the field of building simulation generally is you begin to realise that some of our data foundations can be quite shaky, and that there is a lot of work still to be done to improve that and the quality of the work that we are doing. I'm just going to tell you a little bit about what's coming next now. So we have 3 more sessions left in the occupant-centric simulation-aided seminar series. We have on the 30th of May, we have Fahang Tamasebi, who's going to be presenting on advanced simulation methods for occupant-centric building design, which will cover some of the stochastic methods we touched on just now. On the 20th of June, we will have building interfaces, design and considerations for simulation with Julia Day. And then the finale of this season is going to be on the 26th of June, and we're going to be looking at design of sequences of operation for occupant-centric controls with Burak Güney. And you can see QR codes there to sign up for each of those. And if you don't have time to do that just now, you will also get links to the registration for each of those webinars following this session. So that's not the first webinar that's coming up, though. The next one that we have is the finale of our urban building energy modelling tools webinars. Now, in this series, we began last year by looking at urban scale modelling and some of the philosophical and technical issues involved. This year, we've been looking at some of the tools and a more practical hands-on approach to that. And that's going to continue with looking at CitySim, where we will have Jérôme Kampf and Dasaradin More, who will be talking about CitySim and demonstrating its capabilities and application to a very specific case. And that's on the 24th of May. So do join us for that if you can. If you've missed any of the webinars in this series, they've all been recorded and you can catch up online. In addition to the webinars from this season, we have playlists from previous seasons, and there's a full education on building performance simulation there. So do subscribe to the channel to find out about new recordings as soon as they're released. You can also join the conversation on LinkedIn. If you're not already a member of the Building Performance Simulation group on LinkedIn, there's a QR code here where you can join and do share interesting information, ask questions, and just get involved in the discussion. It's a very lively community. I think we're up to about 11,000 members now in the IBIPSA group, but there's always room for more. And finally, this webinar has been made possible as a result of our supporting members. So do please consider joining as a supporting member of IBIPSA. The fees are remarkably reasonable. I always say they're unchanged since pre-COVID times, which means for $30 for students without the print journal subscription, really very affordable. And those who subscribe as a supporting member have online access to the journal and the right to use the IBIPSA supporting member logo. And you can also pay a bit extra for a print subscription to the journal as well. And you can find out more about that at our website, which is www.ibipsa.org/membership. So all that remains for me to do now is to say thank you very much to Ardeshir. That was another fascinating discussion. Thank you for being so generous with your time and your advice. And I look forward to seeing everybody again next week when we're back for Urban Building Energy Modelling CitySim. Thank you. Bye.